Thank you. Thank you. I think I have on mic. Can everybody hear me? Awesome. My name is Bhaskar, or as I say at Starbucks, my name is Oscar, because nobody can write my name. So that usually works. Thank you, Richard. This is a great opportunity to speak to a very large group of people. When Richard told me there would be somewhere between 100 to 300 people, I was shocked, because I didn't think there would be so many people interested in this topic. But I just wanted to give a very high level overview of what this talk is about. This is not going to be about the depths of machine learning. This is not going to be about the depths of deep learning. What you'll hear is the experience of somebody who, let's say, worked in machine learning 10 years ago, and about 20 months ago realized that, this person did not know anything about deep learning. And at the same time, the entire world was moving towards it. So in spite of having a lot of background in the space, it felt like, oh, I was actually outdated. And so I actually had to go back to the board and start learning. And not only that, at that time I was managing a team of about 50 people, and we had built up considerable expertise, put in a lot of effort to actually come up with pretty good machine learning model. But it was quite clear that it was a matter of time before that would be outdated. So what you'll hear will be less, this is exactly what you should do, but more of, this is what we did, this is what we tried, and hopefully these experiences are useful to you. So just to be clear, classical machine learning, it's actually a term which sort of doesn't exist. So what I'll say is, let's say what existed of machine learning maybe 10 years ago, where everybody who was using machine learning was actually doing one of four things. They were either doing classification, which is taking some data and saying, this part of the data means X and this part of the data means Y. They were doing regression, which basically means I'm trying to predict something based on whatever I've seen so far, and basically extrapolating, as you might call it. Probabilistic models, which is trying to guess the probability of something happening. As you may know, a lot of the work that Google did in the ad space actually depended on probabilistic models. And then many people were using decision trees, etc., which were probably another 10 years old, right? So in terms of techniques, you have things like logistic regression, you have things like decision trees, SVMs, clustering, etc., etc. I would say it was maybe 12 years ago that there was, I think, a big revolution with the Netflix prize. How many people here have heard of the Netflix prize? Cool. So this came out in 2006. Netflix released a data set which was to recommend people movies. And so they released a data set of about 500,000 people and around 20,000 movies. At that time, that was the biggest data set anybody had ever seen in academia. In fact, there are probably 100 PhD theses written just on that data set in the next 2 or 3 years. But that revolutionized academic research, because nobody in academia had actually seen a data set before. In fact, that is when I interfaced with deep learning for the first time, because I had actually been working on exactly the same problem in my thesis. And then as we looked at research, there was a paper from a group in Toronto, and they were starting to use some interesting techniques. They were using what used to be called restricted Boltzmann machines. The math was interesting, but there were some hand-wavy arguments, but the results were phenomenal. So I said, okay, maybe it seems to work in this area. So fast forward to 10 years from now, it's exactly that same group. This is actually Jeff Hinton's group. Many of his students had actually been working on that idea. So why were people using classical machine learning, right? It's actually pretty easy to understand. Most of the time, all of us here have worked with linear equations, right? 10 times x plus 11 times y. If it's less than a certain value, then you predict something, or if it's greater than a certain value, you predict something else, right? It's a very, very easy concept to understand. And so a lot of machine learning that you hear about maybe from 5 or 10 years ago actually was as simple as that. The more complicated ones, whether you look at support vector machines, etc., there was a lot of public implementations. These things were not super complicated. But what was incredible was, because they were so simple, it was possible to scale them many, many times. So I think it was probably the first time that I was at Google that I even learned that data sets of the size of 1 billion existed. And when you have a data set that large, you cannot actually do very many complicated things. And this is when even the compute power was far more limited. So it was only relatively simple systems that could actually scale. So for a long time, it was about taking a very simple model, but trying to use as much data as you could. Right? So that's why I would say in the last 10 years, these techniques actually stood the test of time. And the result usually was, it was a relatively simple model. You could probably see these visualized as sort of circles in a two-dimensional graph, etc. They were actually fairly easy to represent and also very easy to understand. So obviously they had a lot of power. I want to give you guys a few examples that will tell you that will probably explain why this transformation actually makes sense. And this is again going to be relatively simple. How many of you have heard of TensorFlow? Awesome. How many of you have heard of the TensorFlow playground? Okay, so it's actually, if you just Google for it, you'll find it. It's actually a very visual way of just looking at some data sets and trying to understand how to apply machine learning to it. So the premise in all of these is something like this. You have data of 2 dimensions, always between 0, -1 and 1. And then you have something like this. You have all the positive examples. So basically this is x, this is y, x1 and x2, and blue is whenever that's the intent that you want, that's a positive thing, and orange is a negative example. So I would probably have a hard time making an example as such, but whenever you have only 2 dimensions that you're using to make a decision, for example, if you're choosing a restaurant, maybe one dimension could be the distance, the other variable could be the category, and if it's one of the two, you're likely to go there, but if both match your interest, then you're more likely to go there. So something of that form, right? So you can actually try out a bunch of things in this interface, and what I'm showing here is when you have data of this type, which seems to be easily separated by a simple line, right? So this is when you call data to be linearly separable. Linear models or the classical machine learning models do very well, right? Very quickly you'll actually find that a model will learn the exact surface that would separate these two, right? And this doesn't strike as complicated. Even though this, as you may see, there are some oranges in the blue region and some blues close to the orange region. So that's what we call noise. The model is fairly stable, even though there is some noise, right? So if you actually try it out, and you can actually try it out in your browser right now, these models can be trained very, very quickly. And what you'll find is, if the data set is well behaved, then even if you take out a portion of it and you test on it, then training and testing performance can be very, very simple, very, very similar, right? This is probably, this is like the simplest machine learning model that you can build, right? Now imagine you take something of this form, where suddenly the data is not in a line anymore, right? You see one corner having blue and another corner having orange. From a human perspective, it's still relatively easy to separate out, right? But this is where classical machine learning models fail, right? A model actually cannot figure this out, right? And you can see that they start, whatever surface they start predicting, they basically only right half of the time, right? So this is the classic sort of XOR type of problem as well. And in fact, this was the reason why very, very early on, neural networks actually failed. So this is basically the original thesis from 70s as well, which is a model like this cannot actually be learned by a neural network, therefore neural networks don't work. Now obviously a lot of real world data is like this, right?
One question. You said that models like this cannot be learned by neural networks. Why is that? Can you just expound on that?
Because with linear variables, so basically the assumption that you make is they're either strictly increasing or strictly decreasing, and in this case whatever you try to do, so basically if you take a variable x1 and you only can multiply it by a constant, then you're either assuming that as that variable increases you are more likely to be right, or if what you're multiplying it with is negative, that actually means it's less likely, right? So any combination that you try with a simple linear model, it won't work, except if you try doing things like this, which is now you start inserting features which are nonlinear. So this is actually what I feel held up linear models for the last 10 years, which is you can actually start manipulating the data that comes in and allow these models to scale, right? So as soon as you now multiply both of these input variables, a simple machine learning model can simply figure it out again, right? So this is what we call a combination, right? However, in order to figure out that you actually had to multiply x1 by x2 and not divide it or not take the square, etc., you had to look at the data. You had to figure out what would actually be needed to make it work for this particular data, right? Similar example, as you can see now, this again, for a human this is very easy to understand, right? This is simply the inner circle is positive, everything else outside is negative. But the only way that you can get a machine learning model or a classical machine learning model to figure it out is by inserting transformations. So basically using x square and things like that, right? If you tried a linear model with no transformations, again this would fail, right? But then there are still some data sets where anything that you try, it's way too complicated, right? So this is a spiral. Again, as soon as you visualize the data, you can kind of see what pattern there should be, right? But a machine learning model fails here, right? The only way that you can figure out is then again look at the data, figure out what type of transformations you need, and then apply it to your model. And that is my claim, that 90% of what machine learning has been over the last few years is exactly this, which is look at your data, figure out what transformations you need, add it to a model and iterate. And most of the time you'll be wrong, that's okay, you try it again. So it became a lot of trial and error because the fundamental limitations of these models just meant that you had to explore these on your own, right? So these are sort of the challenges that we have observed. This is a summary, and this is the answer to your question as well. So what you basically need is, as a feature, and x1 and x2 were features in our previous example, as long as it's something like this, which means that it is increasing as the likelihood of your output is more positive, which means that you are more and more likely, so it's something like distance in this case, you are less likely to go to a restaurant if it's too far, right? So if that sort of relationship exists, then what a model would learn is simply a line which is basically going to be the intercept for this. So it's going to be something, a straight line like this, right? And bulk of what engineers end up doing, and thousands of engineers have been doing this, it's called feature engineering, right? Look at your data, figure out why your model is not able to pick it up, add a new feature, learn again, right? Now unfortunately, there are still some limitations. So the classic idea behind using non-linear features like the ones that I showed you was it would allow you to scale with data, right? So imagine you train a model with 1,000 data points, you get something. 10,000, get something better. 100,000, million, etc. Now you're getting something very sophisticated, right? I would say somewhere close to 100 million or so data points, you start seeing that another 10x in data volume doesn't actually help, right? So if you take sort of the log of the size of data that you have, what you would expect is that the model would learn more and more and more, but actually it stagnates. So beyond a certain point, anything that you do, the model has basically hit its capacity, right? So these are the fundamental things that in my observation, deep learning is able to address, right? So take a feature like what I just described. A linear model would just fail because there are areas like this where even if you are more likely to go to a certain place based on what the model tells you, you're actually less likely. So imagine something like this. Real world distances tend to be like that, right? It's very likely that you will go in a certain direction, but in another direction you might avoid because you know that place to be very busy, maybe there's no parking available, etc., right? So most of the time, real world problems have features that look like this. You cannot directly use them to predict whether an action will happen or not. And with deep learning, feature engineering is very, very limited, and I'll show you the example. I'll show you examples just after this. And the thesis is, and this is all empirical, that as you keep increasing data size, data volume, deep learning models can actually keep learning more and more. So I'll give you an example, right? So this is the first one of the first examples I was showing, which is the surface that you want to learn is anything close to the center is a positive and everything else is negative, right? So what we are doing here is we're only taking the original variables and we know nothing about the data, but we just add these multiple neurons or these so-called deep layers, and over time, over many iterations, it ends up learning a surface which shows you, okay, that's how it should be, right? Now again, this doesn't appear extraordinary on its own because a linear model was simpler. However, take this example. We have done nothing from a machine learning perspective. It's exactly the same type of model. It's exactly the same feature set, but for a very different type of data set, you're actually able to get very good performance. Right? So the feature engineering work that was needed, you don't need to do it at all. What you've done is replaced it by something like this. And the kicker is examples like these, right? Where again, exactly the same network, nothing else, and you can actually try this, right? Will be able to predict for a far more complicated data set. And this is in 2 dimensions, so it's easier to understand, but you can imagine that if you have now hundreds and thousands of dimensions, the kind of power that these models have, right? So this is exactly what I actually did about 20 months ago when this interface actually came through, which is I was trying to convince myself that there is a reason why my 30-40 person team needs to do something different. And it was not obvious to me because I was not an expert in deep learning. I knew enough about machine learning, but this is where my education was failing me. And there were very few people around me that actually knew the stuff. So as I educated myself and as I actually tried out various ideas, this particular example to me stuck out as, this is the reason why a fundamental move is actually important, because all the hundreds of hours that we basically do dart throwing by figuring out whether this feature will help or that transformation will help, you can just leave it to a model, right? So that was the basic idea, right? So I call it sort of the unreasonable effectiveness, and there this blog post also by the same name. Most real world data is not as nicely behaved as classical machine learning expected. You take a feature and you have to actually divide it into multiple parts. You have to take into account different behavior for different parts of that particular feature, and then you have to sometimes combine it. Because the way we humans make decisions, it's never based on one dimension, it's based on multiple dimensions. So anytime you take human behavior and you're trying to predict human behavior, these models tend to be far more reflective because they can actually do these sort of breaks far more effectively, right? So what we were calling feature engineerings are usually combination, which is you take two variables and you multiply them. That's a combination. Or filter, meaning you only take a certain portion and not all of it. So when you're taking, for example, distance from one place to the other, you can ignore the first, let's say 5 meters or 10 meters, because that doesn't actually make any difference, right? Or transformations, which include squaring, logging, taking any simple transformations like that, right? And these things are all automatically explored, right? So this sounds great, right? So we should just all absolutely immediately move to deep learning, right? So that's the question that I was facing myself as well, which is what do we actually do? I mean, this sounds like too good to be true, right? So this is where the learning part starts, right? It was not obvious in the beginning, but as I look back, these are sort of the buckets of challenges that we faced. One is obviously computational cost. With the data set that we had, we were usually training models in maybe 2 to 3 hours, sometimes half an hour if we were lucky. And by using a deep neural network, that went up by somewhere between 10 to 15x. Right? And so obviously all the resources that we needed, that went up by a pretty significant fraction. There are obviously a lot of techniques that have come up in the last few months to improve these things, but I think this is still a very active area of research. And it helps that we have a lot of improvements in the computation space. We have GPUs coming through, we have very easy parallelization happening, but this is still a very fundamental problem. And the practical reason is this: if you are used to trying out an idea and waiting for it to work, and you want to do it over the course of a day, you need about 2 to 3 hours of iteration time. As soon as that gets multiplied by 10, then practical reasons, you basically have to break your chain of thought. You come back next day, it did not actually work, you try it again, etc. Your iteration time to try out a basic idea goes up maybe non-linearly, square or whatever, right? And so this fundamental challenge actually means that your teams need to be much larger, or you need to be far more realistic about what you can actually achieve. The second sort of main challenge was team and skill sets. Now, as I mentioned, most people actually don't really understand deep learning. I would say it's a fairly limited number. And even more so, people who understand deep learning may not necessarily understand systems as much, right? So you need basically both, because again, the computation part is very expensive and you need to be practical. So you need to have, in an ideal team, a mixture of people who know enough about machine learning and deep learning and are willing to do it, and people who know about systems, right? And suddenly your team structure, your team composition needs to change, right? So in a practical move, this becomes hard. Training and iteration time, as I mentioned, not only is it longer, it's also very hard to know when to stop, because these things take so long. You're not sure if you should, it's been a day, should I stop? Maybe not, I'll give it another day. And then you realize, no, that was actually not true. Right? Maybe you need to stop after 2 hours. Right? Interpretability. So practically speaking, imagine you're responsible in a company and for a feature that, let's say, tags people with photos, right? And you have been developing that system with your team for a long time, and you get user reports saying, oh, the tag was wrong or something of that form, right? Previously, what would happen is if somebody would tell you this was the tag and it was wrong, you would actually go back and see why, right? You would actually try to debug. And usually you would figure out, oh, this feature didn't fire, or that particular feature didn't fire, something happened, and either there was a bug, or it's good news, you actually need to create a new feature because you missed this out, so you change your model, right? But when you have a deep learning system and somebody tells you this particular example doesn't work, you don't really know what to do, because it's so hard to interpret those matrices. So these are all matrices that we were seeing here, right? These are all matrices being visualized. It's very hard to know which of these matrices are wrong or whether they should be different, because every time you train them, you get different matrices, right? So interpretability becomes really, really hard, and I argue that over the long term, this tends to be one of the biggest problems. Right? If you're actually going to work on a system and keep improving it for 4 or 5 years, it's really important that your team really understands what's happening. And finally, I mean, I've kind of covered the reacting to user feedback part, but the long-term complexity is hard to guess up front, because very likely, if you have a successful machine learning system that's been at the center of a product for a very long time, it is very hard to just rip that out and replace it, because the layers above that system have maybe started to make assumptions and say, oh, this system gives me usually values between 0.6 and 0.7. So I'll write that in my code and I'll have that as a constant. But your new system doesn't. In fact, not only does it not, every time you retrain it, it actually comes up with something completely different. So every time you update, the systems above you have to react. And so what starts out with, oh, I'm just going to change this particular class and this particular machine learning model, actually ends up becoming a complete rewrite as far as the assumptions have been made. So I wanted to distill this down to sort of 5 things. If you're actually, so the assumption I'm making is you have a team that's been working on the machine learning model for a while, fairly successful in understanding and also manipulating it. And now this concept of deep learning comes up and you're like, okay, what should I actually do to change? So the first thing that we learned was your first few attempts will fail. I think when my team tried it, I think there were about 17 attempts that basically did not beat the previous system, simply because there had been, I don't know, 2 dozen people working on improving that system for 2 to 3 years. There was a lot of human knowledge that was built into it. It was very hard to beat. And every time that we would actually try something, we would figure out, oh, this reason and that reason, we didn't actually try this idea out, or we didn't try out this architecture, or we didn't have enough layers, or things like that. And also, some of the things that we had learned over time, which was to use features that were cross combinations, etc., actually turned out to be the wrong idea. What you have to do in these cases is to give it as much raw data that is uncorrelated as possible. So it was not about giving it everything, it was actually about giving it fewer basic pieces of information, and that was sort of counterintuitive. All in all, I would say this was maybe 7 to 8 months, let's say 3/4 of work, just to keep iterating and trying out. So if you try out machine learning and it works for you, that's awesome. But if you go from machine learning to deep learning, my expectation generally is you need to give it time before it will actually work for you. The second thing that we had realized is from previous shifts, because even within our existing machine learning system, we had actually moved a couple of times. And every time we had moved, we had to make fairly large changes in our overall architecture. And very small improvements made by, let's say, a very significant change in your machine learning model actually tend to be not as useful, because what we tend to underestimate is how much time it's going to take to rip out something and replace it with something else, right? So we estimated that to actually replace our system with a deep learning system was probably 6 months of work for the team. And if the team had not been working on replacing but was doing something else, what would the improvement in the system have been? Right, so that was about 3 to 5%. So we said, okay, that's our goal. A small set of our team should continue working on learning, but we only switch when the new system is better than the old one by some distance, and about 5% it actually made sense for us. So this prolonged our move by quite some time, but at the same time, what it meant was by the time we actually made the move, enough people understood what had happened, enough people understood that's an iterative process, and it's actually not that different from what they had been doing before from a process perspective. And also these things were not that hard, right? Because it's actually fairly intimidating in the beginning, right? So if it's a small percentage improvement, I would not rip out your existing system. This was probably the hardest one, which is I guess the saying that I believe in is software is easy, people are hard. And so the most of the complexity that you have in your system is actually coming from the people that are associated with it. People are attached to things that they have done. And so anytime you're trying to just improve something with something that's radically different, there's always going to be opposition. So that's one. The second thing is fear. Right? Like we said, most people actually don't understand, or the number may be growing, but most people don't practically understand what deep learning is about. Right? It's not been around as much. It's still the math behind it is still funky. So we actually invested about a week where we said, okay, nobody does anything else except play around with these. And what we did was we created a small data set, a test set within from our previous system and said, okay, this is what you can use, this is what you can train, and then to get the competitive juices going, we actually set up a competition, right? So we created a small list where people would basically say, oh, on this data set, this is what I got. But the commitment was, as soon as you got something, you had to also share your configuration. So think of this sort of as an open source model, right? So somebody tried something, they actually got a decent result, they would post back and say, this is what I tried and that's what I'm getting. So the nice thing was, the next person could say, aha, let me build on top of that. Right? So we had maybe 100 submissions, somewhere around 80 to 100 submissions, and after a while it was clear, in the beginning progress was slow, but after a while there were one or two people who had the background and were making a lot of progress, and people would just start taking what they did and actually trying out different alternatives, right? So I think that had a lot of benefit. People understood that it's actually fairly easy to try out if you know a good starting point, and also it's not that hard. And as they could see real progress being made, I think that convinced everybody. It was not a week that took, a week was just the starting point, but that really told people, this is actually not going to be as hard as needed. And the comparative part helped.
What is the system engineering that are required to do any AI? Can you elaborate? What is the system engineering?
So the question is, what is the system engineering required? So imagine that you are, let's say, a user-facing feature, right? I'll take, recognizing whether the photo that's just being uploaded contains your face, right? What the engineering part required here is to basically do everything that a machine learning model would, but in a reasonable user expectation time frame. So if you uploaded your photo, you would want to use that feature sort of right away, right? Maybe 2 to 3 seconds is what you would expect, right? So the engineering work that's needed is to make sure that you are creating systems that can basically work within those time frames, right? If you're creating a ranking system, that has to respond within, let's say 100 milliseconds, right? With a simple, linear equation, that's super easy. But if you're multiplying, 20 matrices, not so easy. So you have to start pre-computing things, etc. Right? So it really comes from where you're using it. If it's being used for a batch environment, like you are just processing a lot of data, transforming it, the engineering expectation might be, how long can you keep that data? That kind of thing. So it's very very application specific. The fourth learning that we had was improvement. How to actually improve something that you've launched, right? So as I was saying, we spent quite some time, maybe 8-9 months. We came up with a system that was about 5% better than the previous one. We launched it. Perfect. Now what? Now how do you keep improving it? And it turned out that what we had been relying on before was evaluating the system offline and then creating a set of judgment criteria. Okay, if this model is better than this other model offline, then it's a good idea to launch. That surprisingly didn't work as well. And we got a lot of benefit from the offline model because that just meant that you can try out in parallel, 20 people can try out things in parallel at the same time. Within a day or two you would get results. But what we had to do now was to move towards an A/B testing model. And this is where the limitations of the amount of data that we were coming in started to make sense. And also this is where we realized that because this was human behavior data, there was a lot of change in behavior of our users in a fairly short period of time. So if your experiment was running for 2 or 3 weeks, that may not actually be sufficient, right? But we didn't really have any options because with purely offline testing, we were actually getting results that were sometimes counterintuitive. But when we would actually run A/B experiments, they would actually turn out to be positive. So I guess it's a combination of whether it's just A/B testing and also what you show to the users. So in many cases, if let's say the system that you had to take the face recognition example, right? Previously you were recognizing faces 4 out of 10 times and users were responding a certain way. And now you start predicting 7 out of 10 times. User response may change quite significantly, or depending on the application, it may not accept. Sorry, there's a question in the back. So I got a part of the question, but I'll summarize and please tell me if I got it right. Your question is about when you do A/B tests, you have to try out a lot of combinations of hypotheses, and how do you manage that? Yes. So I think that probably goes beyond just what you apply in sort of the deep learning criteria, but generally you're right. You will be able to try out many different options. But I think this is where the benefit that deep learning provides is you are usually not, so in a classic machine learning system, what you would try is, let me add a few new features and see if that works significantly better. What you would try in this case is a completely different network or a completely different model, or maybe some parameters. And I think the number of combinations goes down because, suppose you had 3 features that were being added. Do you actually run sort of 8 experiments, right? Because the effects can be, combined, etc., etc. Whereas in this case, because you're testing out the entire parameter space, I feel like it's not combinatorially exploding. I'm not sure if I answered your question.
Yeah,
your answer was about like a way, like essentially do the hypothesis testing based on the entire parameters or like configurations instead of like making assumptions just on one particular parameter out of many. So like I think like that's very good, like kind of like a high level view, but like in terms of how do we like maybe it's a different topic. We have to have a phase of hyperparameter tuning, right?
Yes.
So like during that process, we want to keep evolving our parameter configurations, however we want to call it. So in this process, we still have so many many iterations we have to handle.
Right.
So how do you like manage this process? You know, you don't want to go back to the old way where manually do everything, right? So how do you do that?
So I think so. The general question is still like how do you basically stay on top of all the parameter tuning that is needed? And again, I think it varies quite a bit from sort of the architecture that you have in and the application. What we found worked for us was establishing again a correlation between what you tried offline and when you tried it online, was there an impact at all, right? So let's say offline you got a 0.1 increase, but online you got 0.5, right? Over enough tests, we could figure out if there is a correlation, right? And then you can essentially go back to offline testing for some of those parameters. If they look really, really promising, then those are the ones that you can go in and test online again. That makes sense? So you basically sort of do hypothesis testing in sort of two phases. Okay. The last one, I mean, this is one that's actually quite close to me, because if you are trying to maintain and improve a system for multiple years, if you don't understand what it does, I think that's a losing battle, right? Unfortunately, there is no easy way to understand these. The best that we could do was to start skipping features out. So let's say you want to understand the impact of, in my example of whether you want to go to a restaurant or not, distance. Then what you try is you eliminate some data and then try it out and see what the impact of that particular of ablation is. And I think that helps in understanding that particular trained network. It doesn't generalize, but it is probably the best thing that we've been able to do so far. The other thing that has helped really is when you're comparing two models, you run them on your test data set, there are always going to be some examples where the new model does better and the older model does worse, right? So these are classical called sort of wins and losses, right? And generally, if you want to launch something that is better than the previous version, then you need to have more wins than losses, right? So most of the time people just do counting, more wins than losses means that's great. What we would suggest, or what we found to be helpful, is actually going into those wins and losses because these are much smaller in number, and trying to extract a pattern by hand. And you can actually build very good tools around this, right? You can actually have that be sort of your entire debugging strategy, which is before you launch something, you automatically produce the wins and losses, and then you try to do some correlations. You know, all of these examples have this particular feature in this range, etc., etc. And generally, if you manage to tune out the losses and so figure out why are those additional losses happening, you will end up with something that's better. If you have a lot of data, or you have the luxury of a lot of data, you can probably avoid this completely just based on sort of the statistical performance that you get. If you are doing very well on a holdout set, that's fine. But if you are not just trying to improve a system, but also build a culture in your team where you are keen to only get something out of the door after people understand and can explain it, then debugging to me tends to be the sort of the most important aspect. And this again relies on heavy sort of iteration infrastructure. Sure. So I'm actually, this was my last slide. So